Let's continue on now with Lecture 5, Presentation 2. What marks primates as distinct from other mammals? Primates are sometimes described as generalized mammals with adaptations for life in the trees. That is such a broad description that it would be applicable to non-primate mammals such as squirrels and sloths. I prefer defining primates on the basis of traits associated with a unique and highly specialized primate feeding adaptation. What sets all primates apart from all other mammals? Primates are the only mammals that habitually bring their food to their faces, not their faces to their food. This unusual feeding behavior characterizes all primates to the exclusion of non-primate mammals. We now need to discuss primate classification. We're going to focus on a very simplified form of classification based on the latest evidence regarding genetics, paleontological field data, as well as primate anatomical and behavioral data. We're going to simplify down to the order Primates and then choose two suborders, Strepsirrhini versus Haplorhini. We'll forget everything going on with the Strepsirrhini and focus in on the Haplorhini, Tarsiiformes, Platyrrhini, Catarrhini, and then we will arrive at the superfamilies within the Catarrhini group, the Cercopithecoidea and Hominoidea. Why are we going at this in such an odd way? Why not learn all of the primate taxonomic units? Well, first of all, there are well over 500 species of primates today, so you don't want to go there. But second of all, there is a bias in this course, and it's intentional. Our focus is on humans. As our focus goes, we go with our classification. We look at our superfamily Hominoidea in comparison to our sister lineage or sister taxon sibling lineage, Cercopithecoidea, the outgroup. Then we're looking at the Catarrhini here, and we're just looking to the Platyrrhini, our nearest non-Catarrhine relatives, in order to understand ourselves. And then the Haplorhini, again, our focus is on the Haplorhini as compared to the Strepsirrhini, and then finally primates compared to non-primates. All of this tells us about the order that humans belong to, the suborder that humans belong to, the infraorder that humans belong to, and the superfamily that humans belong to. Well, when we do this, what we're doing is we're really getting at the distinctions that mark us eventually as human. We share so much in common with all of the primates that we have to parse this out. So let's start out first by stating that the primates today, that is the order Primates, includes the lemurs of Madagascar, the lorises of Africa and Asia, and the galagos or bush babies of Africa. It also includes the tarsiers of Southeast Asia, the New World monkey of the tropical Americas, the Old World monkeys of Africa and Asia, along with their ape cousins of Africa and Asia, and humans. We have a cosmopolitan distribution today, but our origins are in Africa. Now, if we go in, we want to look at the traits of the primates themselves. And so the primates, what are their traits? Then when we go into the suborders, we're worried about the traits that one group does not have and the other group has. If we go to the suborder or the infraorder level, we're looking at the traits that one infraorder doesn't have and the other infraorder does have. And if we go down to superfamilies, we're looking at the traits that are absent in the Cercopithecoidea versus present in the Hominoidea. So our perspective is very biased. It's all about humans. So one more time, let's go through this going from top to bottom. And remember, we're always most focused on the human organism. So the order is Primates. It is represented by two suborders, the Strepsirrhini with lemurs, lorises, and galagos, and the Haplorhini, which includes tarsiers, New World monkeys, Old World monkeys, apes, and humans. We're going to forget about the tarsiers and go down to the infraorder Platyrrhini, which has the New World monkeys, and our infraorder Catarrhini, which we share with Old World monkeys and apes. And then within the Catarrhini, we're focused on our closest non-human relatives of the Hominoidea, the Cercopithecoidea, Old World monkeys. How are they distinct from the Hominoidea, apes, and humans? And we will go further into Hominoidea to understand how apes and humans differ from each other. So what are the traits that join all primates together to the exclusion of non-primate mammals? Well, they are associated with habitual food-to-face feeding adaptations, as we're going to place our emphasis. 1. Forward-facing eyes with nose below. 2. Sight-brained. 3. Stereoscopic vision. 4. Postorbital bar. 5. Nails on digits with tactile sensitivity. And 6. Divergent hallux or big toe for a grasping foot, with one important exception, and that is the humans. We will go over each of these traits in the next slides. The taxonomic traits described here happen to be associated with certain primate adaptations. They allow primates to make a living. Most non-primates don't have these traits. However, there are a few exceptions. When similar adaptations are observed in very distantly related organisms, it is due to convergence. Think of it this way. If two distantly related animals have the same diet and live in similar ecosystems, it would be surprising if they didn't have similar adaptations. This is convergence. Similar adaptations in distantly related organisms. Primate trait 1, forward-facing eyes with nose below. So if we start over on the right with the macaque, you will see that the eyes are above the level of the nose. And when we go over to a mandrill, which is one of the dog-faced monkeys, very snouty, you will see that the eyes are well above the level of the nose. And in an eye, it's one of our little strepsirrhines, a lemur, eyes again are above the level of the nose. And in a gibbon ape, eyes are above the level of the nose. And finally, with my daughter, Katie, her eyes are above the level of her nose. What this does for us is it means that we can see forward without having anything in between our eye orbits. Forward-facing eyes with nose below allows primate eye orbits to sit close together. This increases the binocular field, that is, the zone of overlap between visual fields. The primate binocular field varies depending on which suborder you're looking at, but the Strepsirrhini, lemurs, lorises, and galagos have about 90 degrees for their binocular field, and the Haplorhini, tarsiers, monkeys, apes, and humans, it ranges from 120 to 140 degrees. In contrast, non-primate mammal eyes are placed to the sides of the face with the nose elevated up and between the eyes. A rabbit has a binocular field of about 30 degrees. A rhinoceros must be lower. In a curious example of convergence, some carnivores have binocular fields within the primate range of 90 to 140 degrees. So if we look at wolves and dogs, some breeds of dogs are pretty low, below the level of 90, but some dogs range on up from 90 to 116 degrees. For the cats, most average about 120 degrees. And if you take a look further, you'll notice something. the enlarged olfactory region of the rostrum or nasal region keeps eyes apart despite this overlap. So here's the wolf, and you can see there's this area here separating the eye orbits. Same thing with the German Shepherd, and same thing with a domestic cat. Watch your dog or cat. You will see that unlike a primate, when Fido or Kitty is looking forward, it has to lower its head downward. This brings the eyes above the rostrum and allows stalking behavior. Primates do not need to do this. Primate trait 2, sight-brained. Here we have a curious distinction between the strepsirrhines, like the crowned lemur over on the left, and the haplorhines, like humans. And let's take a look at this more closely. When an anatomical region contributes more to function than a complementary region, it is exaggerated in size. A comparison of the relative size of the olfactory cortex at the front of the brain and the visual cortex at the back of the brain supports this principle. In smell-brained mammals, the cortex ratio is olfactory larger than visual. In the sight-brained primates, the cortex ratio is visual is larger than olfactory. Non-primate mammals, the olfactory cortex is larger than the visual cortex, meaning that they are smell-brained. In the strepsirrhine primates, the visual cortex is larger than the olfactory cortex because they are sight-brained. Let's take a look at this. So over here we have a tree shrew. It is a mammal, but it is not a primate. And you will see the large pink area is the olfactory cortex at the front of the brain. It is larger than the visual cortex at the back of the brain. For the lemur, the olfactory cortex is reduced in size and the visual cortex is larger. The relationship is stronger in the other primate suborder. For the haplorhine primates, the visual cortex is much larger than the olfactory cortex, and they are strongly sight-brained. So if we take a look at the left, we've got a macaque monkey. The olfactory cortex isn't very large, and look at how large the visual cortex is. In the ape, in this case we're looking at a chimp, the olfactory cortex is very reduced and the visual cortex is very large. And then in the human, look at our teeny tiny olfactory cortex. I am surprised we can smell anything at all. And then look at how large our visual cortex is. Strepsirrhines are intermediate. They are less smell-brained than non-primates, but they are less sight-brained than haplorhines. For this reason, lemurs, lorises, and galagos are slightly more scent-driven than tarsiers, monkeys, apes, and humans. Now one of my favorites, primate trait 3, stereoscopic vision. Stereoscopic vision is an adaptation involving the exchange of visual information from both optic nerves at the optic chiasma. Thus, images from both eyes merge together to produce a 3D image. And let me use our highlighter pen here in order to explain this to you. Okay, visual information from the right eye is taken through the optic nerve and gets to the optic chiasma. At the same time, visual information from the left eye is taken through the optic nerve to the optic chiasma. There, they both exchange information, and let me get this one over here, and we end up with parts of both visual areas coming to the back of the brain where they form basically 4 images. As a result, primates can visually measure distance and can detect the contours and dimensions of objects in their surrounding. Those 4 images are brought together and you see in 3 dimensions rather than seeing something flat. So if you cover up one eye and you look at something, it all looks very flat. If you have both eyes open, you get depth, and that is what we're talking about here. Non-primate mammals have limited or no stereoscopy. For example, if you take your dog to a 3D movie, he or she cannot see images popping out of the screen even if you place 3D glasses over their eyes. The dog's brain is not wired for 3D. But there are trade-offs. If the movie was in smellorama, your dog would get more out of it than you would because you have a lousy sense of smell. Primate trait 4, post-orbital bar. A bony post-orbital bar encircles the primate eye and separates the eye orbit from the cheek orbit. The post-orbital bar is easy to identify in strepsirrhines like lemurs, lorises, and galagos. And so if you look at where the arrows are pointing to, that is the post-orbital bar. The post-orbital bar is also present in haplorhines, tarsiers, monkeys, apes, and humans. But unlike strepsirrhines, we have eye sockets. This is because we have eye orbital closure, bony plates of bone within each eye socket. But if you look at where the gold arrows are, you'll see that's pointing to the region of the post-orbital bar. The post-orbital bar protects and stabilizes the eyeball. This is a nice feature for visually dependent primates. Haplorhine eye sockets further protect the eye, but don't forget, haplorhines are also more dependent on vision and sight than are the strepsirrhine primates. Most non-primate mammals have a soft tissue ligament separating the eye and cheek orbits. It is located where the ossified primate post-orbital bar would normally sit. So look at where the arrow is on the left. That is where our post-orbital bar is. In this beaver, a non-primate mammal, you won't find a post-orbital bar. And if you look over at the right, it looks like they just have giant eyes, which beavers do not have. Due to convergence, artiodactyl non-primate mammals, the even-toed ungulates like cows and camels and bison and giraffes, have a post-orbital bar. These are large-bodied grazers. That means they eat a lot of grasses, which generate significant forces and stresses when chewing. This probably favored selection for the trait. So grazing animals, they're chewing constantly. That sends compressive forces up through the eye region, and the post-orbital bar stabilizes the eyeball. Just remember that despite convergence in one trait, carnivore forward-facing eyes and artiodactyl post-orbital bars do not indicate that either is a primate. No one would mistake a cat or a cow for a monkey. Primate trait 5, nails on digits with tactile sensitivity. Primate visual adaptations are related to primate digital adaptations. Before discussing that connection, let's examine our digits, our fingers and toes. Primate fingers are long as a proportion of total hand length. With the exception of humans, primate toes are also elongate. Atop the fingers and toes, primates have flattened nails that free digits from the constraints of claws and hooves. This allows a broad range of digital activities, and I think the next slide will help you out on this. Usually, it is difficult to convey the functional limitations of having claws instead of flattened nails on our digits. However, nail studs have come into vogue and nicely illustrate the problem. With studs extending upward like claws, how could these digits pick up a penny, open a jar, or hold a pen? Okay, they're kind of cool looking, I have to admit it, but fashion that impedes primate function, well, I like having primate nails so that I can pick up fossils. Beneath the padded surface of each digit, primates have specialized nerve tissue, Meissner's corpuscles. This unique feature makes primate digits touch sensitive. So right now, take your fingertip and touch the surfaces around you. You will notice subtle distinctions between those surfaces. Other mammals cannot make those distinctions. They tend to have calluses underneath their digits, and this is to protect them while they're walking. This is a fabulous thing because for primates who are going to use their hands to pick up food and bring the food to their faces, they want to feel what they're lifting up, what they're touching. A primate can feel a tiny grain of sand, can sense the degree of pressure needed to open and manipulate an object, and can delicately groom offspring with fingers instead of using their tongues. Grooming improves health. For example, it can be used to remove parasites, and it also helps primates to establish and maintain social bonds. What you're looking at in this image is a macaque grooming chain. You've got one macaque with a macaque sitting behind it. It's picking through and removing parasites, and another macaque behind that one who's picking through and looking for parasites. Also, if they find a bug in there, they can eat it, so they get snacks. And at the same time, they're giving each other social touch. Primate flattened nails protect the tops of our digits, but they are not useful defensively. Non-primate mammalian claws are much better for defense. However, they impede manipulation, and notice that clawed digits are short. You may have difficulty seeing this because our structures are somewhat distinct, but if you look at the digit area for any of the carnivores, you'll see right here, that's the digit right there. That's the digit right there. And there again. And it's very short, not long and independent from one another. So there's no independent control of those digits either. Claws are not merely long nails. Claws stick upward from the digit. So look at this here, sticking up from the digit. And they are compressed from side to side, and they are triangulate in cross-section, and they are distinct in cell structure. Primate nails simply curve over as they get longer, and they are distinct from claws in cell structure. So histology, they are distinct. For the record, a few primate gum eaters are convergent with clawed mammals because they have claw-like nails. In cell structure, these are true nails and do not stick upward like real claws. They assist with clinging to bark. In addition, many strepsirrhines, these are the lemurs, lorises, and galagos, have a claw-like nail on one toe. It is used for grooming. The relationship between primate visual adaptations and tactile adaptations cannot be ignored. Eye-hand coordination develops during childhood and allows another unique primate behavior. Primates can pick up food with one hand. Think about what this means to us. In our daily lives, we use one hand for one task and the other hand for another task. I typed this presentation while employing eye-hand coordination for separate digital and visual activities. Non-human primates must also have eye-foot coordination. Primate trait 6, divergent hallux, big toe, for a grasping foot, with one exception, humans. So if we look at this lemur, a shafak from Madagascar, that is not a thumb, that's a big toe. And over here on this gorilla, that is not a thumb, that's a big toe, and there's another. The non-human primate divergent hallux allows feet to grasp. This adaptation is associated with arboreal travel and foraging. And I just want to point out with this orangutan, sometimes it's hard to tell feet from hands, but this is a foot right here, and so is this. Note that primates tend to visually inspect food at arm's length before eating it. Let's examine this. So, ruffed lemurs use grasping feet during foraging. Hands are free to bring food to the mouth. And with grasping hands and feet, lorises maintain 3 points of contact during locomotion and can cling to branches while feeding with a free hand. So let's take a look at this in the slow loris at right. Here is a foot holding on to the branch. Here is a foot holding on to the branch. Here is a hand, and here is another hand. And right across here, we have a lizard being eaten like corn on the cob by this little slow loris. Galagos are good leapers. They push off with their feet, which also make a grasping landing. Hands are free to collect and bring insects to the mouth for feeding. And tarsiers are the best and most specialized leapers of all primates. Their grasping feet are extra long, and their eye-hand coordination is so good that they can catch flying insects mid-air. In this case, the tarsier is catching an insect right on a tree trunk, which is almost not fair. The only primates with fully prehensile grasping tails are the 4 heavy-bodied New World monkey groups. And these are platyrrhines. There are only 4 of them with prehensile tails. They include the mariki, as we see over here on the left, as well as the howling monkey, the spider monkey, and the woolly spider monkey. And if you look at the tail up at the top, you can see right here, it's naked. There is no fur on it. This is a frictive surface that will grasp, and they have full control of that tail. Instead of using their feet to take a suspensory posture, they use their tails. Hands and feet are then free to collect foods. No other primates have fully prehensile tails. Thus, Old World monkeys, cercopithecoids, cannot engage in tail suspension. Instead, they use their feet to cling to branches and vines. Their hands bring food to the face. Old World monkeys include more terrestrial species than we find among New World monkeys, where there's really only one, the capuchin monkey, that is comfortable on the ground. The most terrestrial of the Old World monkeys is the quadrupedal patus monkey. It can climb into trees, but it can also stand up on its feet to collect low-hanging tree foods by hand. And notice that this patus monkey is a mom with her baby in tow. Well, apes don't have tails. Unlike strepsirrhines, tarsiers, and monkeys, what they have are extra long arms that allow hand suspension. They can hang by one hand and forage with the other hand. They'll also forage using their feet. And since apes have grasping feet, they can also use foot suspension if the need arises. And here we have an orangutan that simply wants a drink of water. So what about us? Well, like all primates, humans have the traits associated with habitual food-to-face feeding adaptations except for a divergent hallux or big toe. However, humans descend from primates that had divergent big toes. These were the primates that gave rise to today's African apes, the gorilla and chimpanzee, and the first humans about 7 to 6 million years ago. We share that ancestor's suspensory arms, but we are uniquely bipedal, and we'll talk about that more very soon. Now you are ready for Lecture 5, Presentation 3.